Problem number 14. There's a picture here. I assume that you have the picture in front of you. I also kind of drew this as well. I guess I labeled most of the thing here. I just need to draw on that theta as well. Okay, there we go. So what's going on here? There's an official here. There's this car. The car is moving this way. L, X, and Y are labeled as given here. Okay, for the first five parts of this problem, we just are asked a series of questions where we're trying to figure out the signs of various quantity signs, SIGN signs here. So, okay, the first thing here, dx dt, this is the change in x with respect to time, change in this distance here with respect to time. The car is going to the right, and so as time is increasing, the car is moving here, this distance is actually getting shorter and shorter, x is getting smaller and smaller, so that shows us dx dt is negative. Okay, dy dt, this is how far away the official is from the finish line. The official's not moving, the official's just sitting there. So y isn't changing, so its derivative with respect to time is 0. Okay, part C here, dl dt, that's the distance from the car to the official. This is staying put. This is staying put. This is getting shorter and shorter, so L is also getting shorter and shorter. L is getting smaller and smaller. So dl dt is negative. Okay, next up here is what is the sign of the derivative of cosine of theta with respect to t. Okay, so for this one, cosine theta, this is the ratio of x to L. Cosine theta cosine theta is going to be x to L. And so the thing to realize here is x and L are both decreasing here, but x is going to go all the way to 0. Y is going to, if we take a look here, suppose the official is sitting still at the finish line 20 meters from the point where the car will cross. And that tells us that y is 20 meters here. X goes to 0. L gets close to 20. This expression is getting smaller and smaller and smaller. So that expression here, this derivative is also negative. Part E, what's the sign of, now we have a second derivative. A second derivative x with respect to t. Okay, so the car is moving at a constant positive speed here. That means the car is not accelerating or anything. And so the second derivative here is talking about acceleration. There's no acceleration. X is shrinking at a constant rate. The second derivative here is 0. Okay, that's the first 5 parts here. The 6th part has to do with, okay, that's all just setting stuff up. Now we have an actual related rates thing here. Before we crunch out what's going on in F, let me just write down the relation between x, y, and L is x squared plus y squared is equal to L squared. Take the derivative with respect to t of everything in sight, and this is 2x dx dt plus 2y dy dt is equal to 2L dl dt. And we can divide out by the 2's if we want to. Okay, now let's just kind of fill in what information do we have. The official sitting still at the finish line 20 meters from the point where the car will cross. So that tells us y is equal to 20. Okay, suppose the speed of the car is 70 meters per second. So dx dt is negative 70. At what rate is the distance between the car and the race official changing when the car is 60 meters from the finish line? So that tells us x is 60 here. We also know dy dt is equal to 0. We were given that. And L, we can find L because we know x is 60, y is 20. So this tells us that x squared is 60 squared plus y squared is 20 squared is L squared. So that is going to be, let's see here. 60 squared is 3,600 plus 20 squared is 400. So that's 4,000 is L squared. So L is the square root of 4,000 times dl dt. Okay, so 60 times negative 70 plus 0 is equal to square root of 4,000 dl dt. dl dt is equal to, that's negative 4,200 divided by the square root of 4,000. And we're being asked for the units here. The units L is changing in terms of meters per second. So yeah, this is a nice problem. Lots to think through in this problem.